Okay, welcome back everybody from the break. I am happy to introduce Wei Hu from Princeton University, and he's going to talk more about gradient dynamics, but I think from a different perspective. So uh, take it away, Wei.
Okay, great. Thanks. And thanks everyone for joining. And thanks to Adam and other organizers for putting together this great workshop. So today I'm going to talk about my recent work that appeared in this year's New Rips that was last week. The surprising simplicity of the early time learning dynamics of neural networks. And this is joint work with Le Chao, Ben, and Jeffrey, all from Google. Okay. So the previous talk by Nadav has set up the stage really well, which makes my job much easier. So we are interested in generalization in machine learning. And we all learned from our first machine learning course that we should not use an overcomplicated model, which can overfit to the training data, but generalize poorly to the test data. And this goes back to the outcomes razor, which says that more things should not be used than are necessary. And if we translate it into the language of machine learning, it is just simpler models generalize better. Right. But on the other hand, the modern practice of deep learning seems to go against outcomes razor, and oftentimes over-parameterized models or which are highly complex, they often outperform simpler ones. And in particular, in many standard setups, the number of parameters in the model is much, much larger than the number of samples. So for example, it's completely standard to train a network with tens of millions of parameters on just 50,000 examples, for example. So it works just fine and generalizes to the test data. And in these settings, there actually exist many solutions that can perfectly fit the training data, but most of them do not generalize well to the test data. But still, the solutions found in practice can often generalize well. So somehow we can find those good solutions that don't overfit, which is very mysterious. Okay, now to resolve this apparent contradiction, as we already heard from Nadav's talk, we still believe in outcomes razor, and we believe that there's an implicit regularization effect from the optimization algorithms we use. So the proposal here is that the algorithms that we use, such as stochastic gradient descent or gradient descent, prefers low complexity solutions. So in other words, although our model is very complex, but since we are training it using special algorithms like SGD, we will only find a low complexity solution. Okay, so the key open question is, what is the right notion of low complexity in deep learning? So I'll refer to it as property X. So we want to find this property X. So apparently, we need to complete two pieces in order to answer this question. So first, why does this property X imply good generalization? And the second question is, why does SGD find a solution with property X? But unfortunately, as far as I know, there's currently still no satisfactory candidate for property X yet in general. So there have been a lot of attempts to obtain generalization bounds for deep learning, but existing generalization bounds based on various different techniques, they are all vacuous when we actually evaluate them in some realistic setups. And moreover, there's no existing complexity measure that can robustly explain generalization. So meaning that none of the complexity measures can robustly predict the trend of the actual generalization error across different setups. So we are probably still not close to fully understanding generalization in deep learning. But in theory, as always, we can try to start from simple settings for which there's some hope to obtain a good understanding of implicit regularization and the generalization. And hopefully some of the insights there can generalize to more complicated scenarios. So here are some examples of implicit regularization of gradient descent in various examples. So the first example is the simple linear regression. when the number of features is larger than the number of samples. So this is an underdetermined problem, and we know that there are many global minima. And it's easy to show that gradient descent with zero initialization converges to the minimum L2 norm solution. So the implicit regularization of gradient descent there is the minimum L2 norm. And the second example is the logistic regression on separable data. So in that case, one can show that gradient descent converges to the max margin direction. So the implicit regularization is maximum margin. And third example is linear neural networks, which was what Nadav talked about. So as he mentioned, like a few years ago, it was conjectured that gradient descent with near zero initialization minimizes the nuclear norm. But now with more and more studies, we know that it's actually more complicated, and it's more likely that the implicit regularization is something similar to low rank. Okay, and finally, there's a line of work on a type of sufficiently wide neural networks. And there we know that gradient descent with a certain random initialization is equivalent to a kernel method known with respect to a kernel called the neural tangent kernel. So this is also a type of implicit regularization. And I'll talk more about this later since this is related to this talk. Okay, so a hypothesis that's very related to implicit regularization, which takes a more dynamical viewpoint, is that neural network learns functions of increasing complexity during training. So this says that during training, the neural network first learns a simple function, and it gradually learns more and more complex functions later on. Okay, so one concrete example is, again, deep linear network. So we saw from Nadav's talk that in this case, gradient descent can actually gradually increase the rank of the solution during training. So as we saw in this plot from his talk, the singular values, they shoot up one by one during training. So this basically means that the rank of the solution is increasing by one each time. Right, so this is an example. And in this talk, I'm going to talk about a new theoretical result for nonlinear neural network, also along the lines of this general hypothesis. So we will characterize how neural network only learns a simple function in the early time of training. And in particular, we show that in some natural settings, a nonlinear neural network trained by gradient descent only learns a linear function first before it starts to learn anything else. Okay. And this phenomenon was not new. So it was already empirically observed in previous work. And in our work, we will make it more precise and also give a rigorous theoretical explanation. Okay, now let me describe our result at a high level. So our formal result is for two-layer fully connected network trained by gradient descent. So the network looks like this. And we can have essentially any nonlinear activation in the hidden neurons. So I'll describe the precise condition on the activation later. And we also consider a hypothetical process, which is a linear model also trained by gradient descent. So it is basically linear regression. And so this, the linear model is just a vanilla linear model on the inputs with a bias parameter. So it just computes beta 1 transpose x plus beta 2, and beta 1 and beta 2 are the parameters in this model. And we will also train it using gradient descent. And what we prove is that these two processes can be coupled. And specifically, in the early time of gradient descent, the neural network and the linear model compute almost the same function for input coming from the underlying data distribution. So basically, this is saying that the early time of training the neural network can be simulated by doing this linear regression. So in other words, although the neural network has nonlinear capacity, it has nonlinearity, gradient descent will implicitly bias it towards a simple linear function at the beginning of training. So this is a very interesting implicit regularization effect.
I have a question. So, okay, so right now you're saying this is true for any nonlinear activation, but let's say if I just think about the Wei Hu, sure. Then isn't f and n just a piecewise linear function? So look, I mean, when you start moving, you're going to start moving on one of the linear piece, which is indeed a linear model.
Well, I'm saying that it's the same as doing a linear regression for input coming from the data distribution. So that's a non-trivial statement, because like the piecewise linearity is only like locally for say some region of in the input space.
I'm not sure I understood.
Yeah, so maybe it will be more clear when I describe the precise statements.
Sure. Okay.
But also this holds not just for ReLU, it's for any nonlinear activation essentially.
Okay.
Great. Yeah. So now, before going to the precise statements, let me show you some experiment to verify this result. So we train a 2-layer neural network on some synthetic data. So this is a setting that can be covered by our theoretical results. And we also train a corresponding linear model that's predicted by our theoretical result. So this plot here shows the losses during training for these two models. So for the neural network is in blue and the linear model is in red. And we can see that the neural network and the linear model indeed have almost the same loss in the early time. And this is true for both training loss and test loss, so they all coincide here. And this agreement between the two models lasts all the way until the optimal linear model is found. So at about 1,000 iterations, the optimal linear model is found. So the linear regression in red will stop making progress after that. And after this point, the neural network will continue to make progress. So it's learning something nonlinear. Okay. And to see this phenomenon more clearly, this right plot shows the output of the neural network and the linear model on 5 random test inputs during training. So we can see that even on every individual input, these two models give basically the same outputs in the first 1,000 iterations. So this suggests that the neural network is really computing a linear function over the data distribution. Cool. And also actually this phenomenon is more general and we can see it on more complicated networks and realistic data sets. So here I'm showing a 4 hidden layer fully connected network and a 4 hidden layer convolutional network trained on the CIFAR10 dataset. That is a standard image dataset. So similar as before, we plot the losses and the evolution of the outputs. And we can see that both of them can be well simulated by training a linear model. So this left plot is slightly different from before. Here we are decomposing the loss into 2 parts. So the solid curve is the loss on the linear subspace spanned by the data, and the dashed curve is the loss on the orthogonal complement of that subspace. So we're doing that because we know that the linear model cannot learn anything on the orthogonal complement. So it's shown in this red dashed line. And now with this decomposition, we can see very clearly that in the early time, the neural networks are also not making any progress in the complement space. So which means that they're essentially learning a linear function up to this point. Great. So now I'm going to describe the formal setup and the results, and then I will give a proof sketch and I'll discuss the extensions of this result. Okay, now let's start with the setup. So we consider a 2-layer neural network, and the input dimension is D. So the input is X from RD, and we let M be the width of the network. So that's the number of neurons in the hidden layer. And we let the first layer weight be W, which is an M by D matrix. And the second layer weight is V, which is an M-dimensional vector. And the output of the network is this function of the input and the weights, W and V. So this is a standard 2-layer neural network, and there's a nonlinearity phi applied on every hidden neuron. So there are these scaling factors, 1 over root M and 1 over root D. They are due to the so-called NTK parameterization. And so in this parameterization, we can initialize all the parameters with variance 1. And these scaling factors can make sure that the variances at the hidden neurons and the output do not blow up at initialization. Okay. And the specific initialization we use is this anti-symmetric random initialization, which was used by several previous works. So here, what we do is to divide the network into two halves. And the first half, which is neuron 1 through m/2, is initialized randomly. And the second half is initialized as the opposite of the first half. So basically, this can ensure that the output of the network is always 0 at initialization for any input x. Okay, so this can make things a lot cleaner, and usually by doing this, we can actually improve the performance. So this is the setting we will work with. Okay, so now for the activation function phi, we require that it's either a smooth function, and specifically we need it to have bounded first and second order derivatives, or it's a piecewise linear function like ReLU and leaky ReLU. So this covers all the commonly used activation functions like ReLU, sigmoid, tanh, and so on. So basically this means we can allow any nonlinear activation. Cool. So next, I will specify the assumptions on the data. So we have n samples xi, yi from 1 to n, drawn IID from weight distribution, and xi's are the inputs and yi's are the labels. And we assume that the input has 0 mean and covariance matrix sigma. So I write Gaussian here, but it's not important and can be generalized to sub-Gaussian or some bounded moment conditions. So this is basically for the purpose of some concentration arguments used in the proof, but we don't need to worry about them today. And we also assume that the trace of the covariance sigma is normalized to the dimension d. And also all the eigenvalues of sigma are of order 1. So this means that the covariance is well conditioned. And we assume that the labels are bounded, but other than that, there's no other assumption on the labels. So basically, we don't assume anything on how the labels are generated. Okay, so then under these data assumptions, it's very standard to show several concentration properties that's satisfied by this input data if the dimension d is sufficiently large. So first, the norms of the xi's are concentrated around square root d. And second, every pair of xi and xj are nearly orthogonal to each other. And we let third, we let capital X be the n by d data matrix. Then the empirical covariance matrix, which is 1 over n x transpose x, should also have all the eigenvalues of order 1 because it will concentrate around the true covariance, which is sigma. Okay, and this property requires n to be larger than d. So here we just assume that n is greater than d to the power 1 plus epsilon for some small constant epsilon. And throughout, we will also assume that n is upper bounded by polynomial in d. Okay, so that was all the assumptions. And we use the standard L2 loss function for training, which is defined here. And for now, we just consider gradient descent only on the first layer weights W. So we fix the second layer V to initialization and only update the first layer W using gradient descent with learning rate eta. And we do have similar result when the second layer is also trained, but that one is slightly more complicated. So I'll go to that later. So for now, let's just train the first layer. Okay, and finally, we let ft be the network, be the function computed by the network at iteration t. So it is defined using the weights at the tth iteration. Cool. So remember that we want to couple the neural network training with a hypothetical process of training a linear model. So now let me specify what is the linear model. So the linear model is the f-lin defined here. So as I promised, it's a linear function on the input x, except that there's a scaling factor 1 over root d and some scaling constants zeta and nu. So these are definitions of zeta and nu. They are constants that depend on the activation function, And nu also depends on the data covariance sigma. Okay, so these factors basically enable us to use the same learning rate eta here as in the neural network training. So if we don't want these scaling factors, we can remove them, but then we need to adjust the learning rate appropriately so that we still get the same dynamics. Okay. So, but anyway, this is still equivalent to doing the linear regression. And we still use the L2 loss, and we update the parameters beta using gradient descent starting from 0. And finally, we let f lin t be the linear model that we obtain at iteration t. So now we are ready to see the result. So remember that our goal is to prove that these two processes are close to each other. So basically, we want to prove that ft and f lin t are close. So here is the precise theorem. So we assume that the width m is greater than d to the power 1 plus epsilon for some small constant epsilon. So basically, we want the width to be slightly larger than the input dimension. And for the learning rate, we need it to be smaller than order d. And I'll say what that means later. And then for all iterations t from 0 to this capital T, which is d log d over epsilon, we have that the neural network ft and the linear model f lin t are close in the following sense. So first, they are close on the training data x1 through xn. So we show that this mean squared error on the training data is smaller than like d to the power minus omega epsilon, because we assume epsilon is a small constant. Then when d is large, this error will go to 0. So these two models make basically the same predictions on the training data. And second, we show that they're also close on the underlying distribution where the data are drawn from. Okay, so we show that the expected squared error, also with a truncation, this expectation is small. Okay, and the expectation is for x drawn from the input distribution. Okay, so the truncated loss here is for some technical reason, which I think might not be very important. But anyway, this is still a valid choice of loss. And this result qualitatively means that ft and f lin t are close on the entire input distribution. Okay, let me mention a few remarks. So in this result, we have this agreement between the two models up to iteration capital T. So we need to understand what this means. And actually, after T iterations, the linear model f-lin will already reach a near optimum. So notice that this is just a linear regression, so it's very easy to show this convergence. So this means that the neural network first exactly learns the optimal linear model. So that's because we know that at iteration capital T, the neural network is close to the linear model, and the linear model will basically the same as the optimal linear model. So in other words, the neural network performs the entire linear regression before it does anything else. And second, I want to emphasize again that there's no assumption on the labels yi. So whatever yi's are, the neural network will try to do a linear regression to fit the yi. And the third remark is that the width requirement that we have, that width is slightly larger than the input dimension, is a very mild assumption, and that's typically satisfied. So we don't need the width to be very large. In particular, we don't need it to depend on the number of samples. And I'll say more about this point later. And the final remark is that about this learning rate, we need it to be smaller than order D. And the order D is actually the largest stable learning rate. So that means if the learning rate is much larger than D, the training will be unstable and the loss will blow up. So our result can allow the largest possible learning rate within a constant factor. Okay, is there any question at this point?
So is it clear what happens after capital T?
No, it's not. No, we don't have any characterization of that.
So it doesn't follow from any result for NTK that something better happens
No.
after.
Yeah, so
Okay.
if the width is super wide, we know it follows the NTK, but if not so wide, then it can differ from that.
Thank you.
Yeah. Cool. So now I will give a sketch of the proof. So our proof, as I said, is inspired by the theory of NTK, neural tangent kernel. So I'll first very quickly explain what that is. So the NTK theory says that a sufficiently wide neural net trained by gradient descent is equivalent to a kernel method with the neural tangent kernel. And so we probably all know that the idea of kernel method is to map an input x to some other feature space hx, which can have very high dimension or infinite dimension. And the kernel method is to try to learn a linear function of h. And we can do either regression or SVM in this feature space. And the kernel trick says that in order to do that, we only need to compute this kernel function, which is the inner product in this feature space. And we don't need to actually work with the feature space, which can have very high dimension. Okay, so now the main idea of NTK is to consider a linearization of the network around the randomly initialized parameters. So what does this mean? We let fx theta be the neural network. So the theta is the parameters and x is the input. And we also let theta init be the parameters at random initialization. And what we do is a first order Taylor expansion around theta init, and we will get this. And notice that we can ignore the first term because recall that we can make the initial output 0 by doing this anti-symmetric initialization. So we don't need to worry about this 0th order term. So this is the approximation we get. And now if we just pretend that this approximation is accurate, then this right-hand side is actually linear in the parameters theta. And we can view it as a linear model in this blue feature vector. So the blue feature vector is the gradient of the network with respect to the parameters, and we evaluate it at the random initialization point. So corresponding to this feature is this kernel function, and this is the so-called neural tangent kernel. Okay, and so if this approximation is accurate, we know that we will get a kernel regression with this kernel, and we still need to justify this Taylor expansion. And in fact, we can show that if we run gradient descent, this approximation will be valid during the entire training process if the neural net is sufficiently wide. And the width requirement, the width there usually needs to be very, very large for this theory to hold. For example, most of the time it needs to depend at least polynomially on the number of samples and also some other quantities. So this is a much more unrealistic assumption than what we assumed in our theorem. So recall that we only need the width to be larger than the input dimension, and we don't need it to depend on the number of samples. And okay, so that was a quick summary of NTK. So when this NTK theory holds, because we know that we are doing a kernel method with this kernel K, we know that the kernel matrix capital K, so which is the n by n matrix that contains the kernel function evaluate on all the training samples x1 through xn. So this kernel matrix will determine the behavior of training. Okay, so now the main idea in our proof is to show that the neural network and the linear model have similar NTK matrices. Okay, so these are the two models. So first we can compute their NTKs. So by the previous definition, we just want to compute the kernel function corresponding to this gradient feature. So here we only need to take the gradient with respect to W because we are only training the first layer W. And this is the expression we get for the kernel function. And for the linear model, we can also easily compute the kernel function, this K-lin, which is basically just the inner product. Okay, and then we can compute the matrix, the kernel matrix on the training data. So which is this capital K. So that's an n by n matrix. And also here for the linear model, we can also compute the kernel matrix K-lin. So it's just a linear combination between the linear kernel XX transpose and the O1 matrix 1-1 transpose. Okay. And now we want to show that these two matrices are in some sense similar. And what we show exactly is that is this key lemma. So the lemma says that with high probability over the randomness in the initialization and the randomness in the training data, we have that the difference between these two n by n matrices, K and K-lin, the difference has operator norm upper bounded by n over d to the 1 plus epsilon. Okay, so now let's look at what this lemma means. So I will illustrate it using this plot, which shows all the eigenvalues of K and K-lin in an example. So here, the eigenvalues of K are in blue, and the eigenvalues of K-lin are in orange. So notice that first, this matrix K-lin has rank only d plus 1 because XX transpose is rank d, and the O1 matrix is rank 1. Okay, so that's why in this plot, we see that K-lin only has about 100 non-zero eigenvalues. That's because d is 100. And moreover, we know that all the non-zero eigenvalues of K-lin should be of order n over d. So that's because we know all the eigenvalues of XX transpose should be order n from the concentration of the empirical covariance of the data. So that I previously showed. So also this 1-1 transpose also has eigenvalue order n. So this entire matrix have all the non-zero eigenvalues n over d. Okay, now if we look at this lemma, what it says is that K, the kernel matrix K, is equal to K-lin plus this perturbation matrix, and this perturbation only has operator norm bounded by n over d to the 1 plus epsilon, which is much smaller than n over d when d is large. So that means that the perturbation will not affect the top eigenspace of K-lin, and it may create many small eigenvalues, but the small eigenvalues are all smaller than n over d to the 1 plus epsilon. So this is why we are seeing this eigenstructure of K, where the top eigenspace is the same as K-lin, and also there's a clear eigengap between these top eigenvalues and the other small eigenvalues. So this is implied by this lemma. Okay, so now with this lemma, we can finish the proof in a few more steps. So first, if we were to do a kernel regression with the kernel K, then the proof is done. So this is because in kernel regression, we know that the top eigenspace is learned faster than the bottom eigenspace. And here, because there's a significant gap in the eigenvalues, there will be some point where almost everything in the top eigenspace is learned, but almost nothing in the bottom eigenspace is learned. So at that point, because the top eigenspace is basically the same as K-lin, we actually know that what we learn is a linear function. So we are doing a linear regression. Okay, so now the second step, because we're not really doing kernel regression with K, we are training a neural network. So we still need to show that training the neural network before iteration T is close to doing this linear regression. And in order to show that, we need to show this linearization approximation that I showed when I introduced NTK. We need to show that this approximation is accurate in some sense. So actually, we have to show this very carefully, and for our theorem to work. So we actually need to bound the average error over the training data, as well as some imaginary test data. So the point is that we need to do this very carefully, and we just if we only bound this error on every individual data point, we will get a much worse width requirement. We will not get m greater than d. Okay, and there are a few more technical remarks. So the first one is that the reason that we only require this a very mild width requirement m greater than d is because we only care about the top eigenspace of the kernel, and we only care about the early time of training. So in other words, we don't say anything about what's happening in the bottom eigenspace. So as long as the top space is not affected, our result will be valid. And the second remark is that we could try to more naively bound the operator norm of this difference by like bounding the Frobenius norm, but that will not be enough because the Frobenius norm will scale like n over d, and this is tight. And if we use this as an upper bound, this will not be enough for our purpose because it can mess up with the top eigenspace. So the point is that we have to bound this operator norm in a more careful way than bounding the Frobenius norm. Okay. Is there any question?
Wei, I didn't see where you used any properties of the activation. If you were to just do kernel regression, are you?
Yeah. So the yes, we are. So that's why it's a general property that holds essentially for any activation. But the zeta and nu constants here, remember that they depend on the activation function. So like for any activation, we can have this kernel, and we show that it's approximately the same as a particular k-lin. So but the constants here depend on the activation.
Okay.
Yeah, that's the only place this comes in. Cool. Actually, in fact, like for some activation functions, this zeta will be 0. For example, if say if you look at the sine function, sine or cosine, for them this zeta will be 0. So that means that we will not be able to learn a linear function. Yeah, but for as long as this is not 0, this property will hold. Great. Yeah, so that was the result for training the first layer. And now we will move to training the second layer only. And after this, it will be very clear how to handle the case of training both layers. Okay, so now we fix the first layer to initialization and only train the second layer using gradient descent. So what changes now is that we will have a different corresponding linear model for this process, which is defined here. So I put linear in quotes because I lied before. This is not exactly a linear model in the input x. That's because there's this additional blue coordinate here, which depends on the norm of the input. Right? So this linear model is linear in x as well as this blue feature. So in this blue feature, you may notice, so these are the constants that appear in this definition. So again, they depend on the activation function. So you may notice that these last two terms only have smaller order than the first term because of this concentration property of the norm of the input. But it's still necessary to include these two terms, and otherwise the theory will not work. And yeah, we actually construct an example to illustrate that it's necessary to include this norm-dependent feature. So here's the example. So in this example, we let the labeling function to generate the data explicitly depend on the norm of the input. So this is the function that we use to generate the data. And this plot shows the test losses of 3 models when we try to fit this data. So the first model is the neural network with ReLU activation, which is in blue. And we train the second layer of this network. And the second model is this red one. It's the linear model predicted by this theory. So this is exactly what I write here. This is in red. And the third model is a naive linear model, which is the same as this, except that we remove these last two terms, which depend on the norm of the input. So it's the naive linear model is a real linear model on the input. And clearly here we see that the linear model that we predict is a much better approximation to the neural network than the naive linear model. So this is reasonable because we expect that this feature can help learn this label that depends on the norm of the input. Okay, so this means that it's necessary to include this nonlinear feature in the definition of this linear model. Okay, so that was the case for training the second layer. So now with these results for training first and second layers, it's very easy to obtain the corresponding linear model for the case of training both layers. So basically, we can just combine the previous two linear models and get the corresponding linear models here. So that's because the NTK for training both layers is the sum of the two NTKs for training the first layer and for training the second layer. And it's very easy to write down the corresponding linear model whose kernel is the sum of the previous two linear kernels, right? And also we can allow different learning rates in both layers. So that was for the same learning rate. If we have different learning rates in two layers, we will just get a weighted combination of these two NTKs. And of course, we can, in a very straightforward way, write down the corresponding linear model to respect this weighted combination if we have different learning rates. Right. So finally, let me briefly mention some extensions. So we saw that the general principle behind this linear learning behavior in the early time of training is that the top eigenspace of NTK agrees with the linear kernel XX transpose. And we have some more theoretical evidence which shows that this property also generalizes beyond two-layer fully connected networks to multi-layer fully connected and convolutional neural networks. But the theory, especially for convolutional network, is not complete yet. And but we can already verify this behavior empirically. So like including even on real data sets. So like what I showed in the beginning, I showed some experiments of multi-layer convolutional nets and fully connected nets on the CIFAR10 datasets. And we can also try to explain this behavior for real datasets because we can still look at their corresponding NTKs and to see if this top eigenspace agreement behavior is still true. So for example, here I'm showing the eigenvalues for K and K-ling for the MNIST and the CIFAR10 dataset. So what we found here is that there's still a pretty clear agreement between the kernels, but it's not as nice as the synthetic data that we saw before. And in particular, there isn't an eigengap in the spectrum. But still, this agreement can explain to some extent why we are seeing the same linear learning behavior on these real data sets. Cool. So now let me conclude. So we proved a new result that characterizes the implicit regularization of gradient descent. So we showed that in some natural settings, a nonlinear neural network does linear regression in the early time of training. Okay, and we saw that the underlying reason for this phenomenon is the top eigenspace agreement between the NTK of the neural network and the linear kernel. And this phenomenon seems to hold quite generally. And on the technical side, we also saw that the theory of NTK, which was originally used for studying very wide neural networks or infinitely wide networks, it can still be useful even at a small width if we are trying to characterize the early time of training. And finally, a very interesting question, which was asked during the talk, is that what happens after the linear learning period? And we know that this period cannot be characterized by the NTK anymore because the width is small, and we see that the NTK can change a lot. So what is it? And that's all I have.
Okay, thank you very much. Any questions for Wei?
Could you talk a bit about the role of the imaginary test points in your approximation?
Yeah, sure. So we want to show like these two models are close on the entire distribution. And but here, maybe let me go to that point. So here, like this closeness between the neural net and this linearized approximation, if we want to show the tight behavior of this approximation, we need to show it on average over some training data or over some test data. But it's not enough to show it on individual data points. So that's why we take imaginary test data sets which contain many test data points, and we show that they're close on average on those test data points, and then we move it back to the entire data distribution, like using a concentration argument. But I don't think that approach is necessary. I don't think so. I think we can directly handle the test distribution.
So I'm confused about the fact that I thought your theorem did claim that if you only average over the training data, the two like the linear and the neural net are close, right? You made a claim both about the training set,
yes,
and separately about the test set.
Yes. So the test set is for showing the agreement on the data distribution. So the imaginary test data is used for showing the second prop statement.
For the so on the average over the training, it holds then? Just
on the training data it holds. Yeah, we don't need test data. Yeah, this is only for showing the generalization, basically.
Any other questions? Okay, we'll meet back in 13 minutes, and Satan will give us more of an algorithmic perspective on these topics. See you then.